So hello everyone, this is Luboš Pirkl from CFD Support. I'd like to welcome you to the webinar where we are going to show you a validation of CFD simulation results of the Potsdam Propeller test case using TCFD together with the Pointwise mesh. I hope everything is working well. We are running live, so in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. The webinar is being recorded and the recording will be made later publicly available. We have a lot of stuff to show, so make yourself comfortable. Please do follow carefully and think about what it is that you need to improve your simulations and tell us. At the end of the webinar, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar, and it will be our pleasure to answer them, or you can even send us an email later and we will be happy to help. And what else? I think it's time to get to the action. So maybe right at the beginning, I'd like to stress out that this is a two-way webinar. There are two independent companies, this Cadence Design Systems and CFD Support. So we have in fact, we have nothing in common, but we have synergic products that work very well together. So Pointwise is an advanced tool for creating high-quality meshes for CFD, and TCAE is a simulation tool, a simulation environment aimed primarily on turbomachinery and external aerodynamics simulations. So that's for the beginning, and so please let me start with the webinar speakers. So this is me, my name is Luboš Pirkl, and my current job is telling the world about CFD support. And together with us on the line, there is an American cowboy, Daniel Lacroix, who is lead application engineer at Cadence Design Systems, responsible for Pointwise. Hello, Daniel, can you hear us?
I can hear you.
That's great. So how are you? How's it going?
I'm good. I'm excited about today. Looking forward to discussing this.
Right. So it's morning in the United States, in Texas, right?
It is 8:03 in the morning right now. I'm drinking a cup of tea.
Perfect. So you are having your day ahead. What's the, by the way, where you located? It's in Dallas, or?
I'm located in Fort Worth, which is about 30 miles west of Dallas.
Okay, so it's not I knew it, but it's not a part of Dallas, of the city. It's a completely separated area.
It's a completely separate area.
Another city.
But it's another large city. So I think the 15th largest city in the U.S. So
great. Okay. By the way, do you know what comes what comes on mind in Czech Republic to people when you say Dallas? Would you guess? It's not a city.
I would guess the TV show.
Yes, exactly. That's what I meant. Yeah, you're smart. Yes. It's a TV show. It was extremely popular in 90s in Czech Republic, and Dallas, it's a TV show. Yeah, it's funny. Yeah. Great. A pleasure to have you here. Great. And let's go a little bit ahead. The next speaker is Radek Máca, who is our head engineer here at CFD Support. Hello, Radek, are you with us?
Yeah. Hello, I am directly sitting next door to you. So hello. And hello to everybody in the hall, from sunny Prague at 3:05 p.m.
Yeah, great. So if Daniel is an American cowboy, then Radek is totally a golden boy. Yeah, CFD Support with golden hands. So are you? How is your new motorbike?
Yeah, it's still really good. Yeah, so I'm looking forward to take a ride after this webinar. So.
Okay, right. And are you still selling your old one, the old motorbike?
Not decided yet. Yeah.
Okay. So
I'm a little bit repairing it, so I'll
yeah,
see.
you could make some promotion here. Maybe you would find a buyer.
Okay, so next time I think we have more important things to do right now.
Okay.
Right?
Okay. You're right. You're right. So let's do that. Okay. So great. So here's the agenda of today's webinar. Yeah, there will be. It's simple. There will be like 4 parts. In the first part, there will be this webinar introduction, and it's approaching to its end. There will be a meshing part where Daniel will show us the meshing stuff and things, how it works with Pointwise. Then there will be naturally the simulation part where Radek will show us about or tell us about the simulation. And in the last part, as announced, there will be a Q&A session dedicated to your questions and answers. So feel free to ask your questions, and we will be happy to answer your questions. We will answer some of them. We will answer right away in the webinar, and the rest of it will be answered later via email. So you can be sure that all the relevant questions will be answered. So it's your time. So use it to the fullest and ask. We'll be happy to help. It's our job, and after all. Okay, so this will be, yeah, that's the agenda, and I'll just say a little bit about what's the object. So we in the beginning we wanted to make something which is quite transparent and available. We wanted to show a very advanced kind of simulation on a very advanced mesh in Pointwise, created in Pointwise, and let's say the very best of the simulation of CFD. And we were in the beginning we are looking for appropriate test case, and we have found this Potsdam Propeller test case, which is very good test case for our purposes, because it has been measured. It's a real facility. It was measured in a real facility in SVA Potsdam, in Germany, in Potsdam. So the data, the measurement data are available. The geometry is available, and all the case is extremely transparent and clear, and it's repeatable anytime, and it fits our purposes very well, I would say, because as you know, a typical benchmark has an issue of confidentiality of the data, which are typically the client's data, which are untouchable. And this one is transparent, and the beauty of this test case is anyone can take it and repeat it anytime, and you can check again and again it works, and how it works, and what's its performance. So what we did, we asked our friends at Pointwise to create the mesh, and here at CFD support we have run the simulation, and we would like to show you how it worked and what are the results. Yeah. And yeah, maybe the last time, all the resources, last thing is I wanted to say is all the resources are available. There is a PDF where you can read all the important details. So it's certainly available. So feel free to yeah, take a look. Okay, so now it's time for the meshing part of the webinar. So I'll hand over the presentation to Daniel.
Perfect.
So,
all right. So as Lubo said, my name is Daniel, and I'm a lead application engineer at Cadence Design Systems, and we have been developing Pointwise, which is a program that's been in development for over 25 years, and I was responsible for the mesh. And so to start with, I'm going to show the whole flow domain, and I use the dimensions here for a reason. I did it in terms of the diameter of the propeller rather than just putting raw dimensions, because Pointwise is dimensionless. Could have been dimensioned in meters, feet, inches, miles. We don't really care as long as it's all relative to itself. So speaking about the CAD itself, For the most part, it was pretty solid. It was good. Most of the surfaces were rather smooth. We did have one area, and this is at the edge of a blade, and of course there's 5, where it left a little to be desired. And usually when you bump up against some rough CAD like this, you have a few options. And if you have a good CAD package, you can take it into there and fix it, or you could talk to your CAD guy and ask him to fix it. We have a few tools in Pointwise that can handle something like this, but for this particular instance, I used a different technique. I used a technique called fault-tolerant meshing, in which point we put a smooth grid over top of this kind of rough-looking CAD, and then we grow the volume domain from there. Pointwise is a bottom-up mesher, and so we can do that. Which gets me to the surface mesh. We used the Delaunay algorithm for the isotropic surface mesh, triangles only. Pointwise can handle mixed cells. We could have done the combined cells here. And there's also other algorithms that are available in Pointwise, such as advancing front ortho. But for this, we mostly just stuck to Delaunay, and we kept a fairly high boundary decay. So what that means is that the number of points on the boundary on these blue lines carry fairly far into the domain before they start broadening and getting bigger. For areas of high curvature, like on the blades, we use a technique that we refer to as T-Rex. Now, T-Rex in 2 dimensions, the user can specify an initial step height, and anisotropic triangles are grown off of a boundary edge. And the user can also specify the growth rate, and these anisotropic triangles are gradually stepped until they reach isotropy, and then that Delaunay algorithm that I've already shown takes over for the remainder of the area. You can see it's done here on the gold portion. It marches in all the way to isotropy. The green portion is the fault tolerant I was referencing a couple slides ago. But for this technique, we laid a structured domain over it, and then we took that structured domain and we cut each cell in half to make 2 triangles. It's a technique we call diagonalization. It's a tool we call diagonalization. And you can see that that was done here in green, on the green portion. Overall, we had about 600,000 surface cells with a maximum angle of a little more than 130 and a maximum area ratio of a little less than 4. Overall, we were happy with this surface mesh. That was a really strong quality surface mesh. And with that, we built our volume mesh. Now, this is a cut obviously straight through the propeller, and you see there's 4 different cell types that are utilized here. The first I'm going to talk about is the red tetrahedrals. That was the bulk of the domain once you get away from the propeller itself. The prisms, which is a portion in green, are formed by that same T-Rex algorithm, but rather than it being in 2D, this was in 3D. So rather than stepping to make triangles, which is a 2-dimensional shape, these step to make tetrahedrals, anisotropic tetrahedrals. Same situation, the user can specify the initial step size, the growth rate. Even more than that, they can especially set specific stop criteria, and the algorithm can stop locally rather than as a universal front. So that's why you may see little areas where the prisms extend a little bit further into the mesh. Again, the goal is to reach isotropy, and then it transitions to tetrahedrals. After all of the anisotropic tetrahedrals are created, they're then combined for cell reduction to make green prisms. If the T-Rex algorithm is grown off of quadrilateral cells, the cells are then combined to make blue hexes, which explains why there's a few blue cells there around the shaft. The yellow pyramids are there simply for transition regions to go from prisms or hexes to the tetrahedrals. For a picture of the greater flow domain, we have the region around the prop, which we already discussed. There's about 12 million cells there. A little bit further downstream, there is a rotating reference frame region, and that is made up exclusively of tetrahedrals. There's about 2.6 million there. Outside of that is the stationary region, and that is mostly TETs. There's a few prisms adjacent to the shaft, again, using the T-Rex algorithm and some cell reduction, so we could capture any boundary layer phenomena there. And that brings us to the stats. All told, there was about 17 million cells for this mesh. The maximum angle was a little less than 170, and the average was closer to 100. The maximum volume ratio, we did have a few outliers closer to 30, but that was atypical. Most cells are closer to an average of 1.5, and the maximum centroid skew was about 0.86, but the average was closer to 0.123. And this image shows a nice look at how T-Rex can be stopped locally and then grown to much further distances away at other locations. So with that, I will pass it back to Lubos.
Okay. Thank you, Daniel, for this part. I'll take back. So just let me know when you see my screen.
We see your screen.
Okay, very well. So I'll continue with the presentation. So we have learned about the mesh, and okay, I'll slowly continue with the simulation part. So I guess you know our company CFD Support was founded in 2009, and it's located in Prague, Czech Republic. Our main field is simulations, primarily CFD and FSI simulations of engineering, of various engineering problems all across the industry. And our main, our golden egg is a product which is the simulation tool. We call it, sometimes we call it a simulation environment, because there are a lot of components you can combine and play with. And in fact, it's a set of standalone software pieces. We call them software modules, and you can combine them together. No matter what other pieces of software is used together with it, it still works very well with all various commercial codes, with in-house codes, and with other open source. It's based on open source, which is common knowledge. And TCAE has a strong integration ability, so it fits existing workflows, and it's definitely ready for big industrial challenges nowadays. I'll be very quick here, because Radek is waiting for his part. I know it. So I'll just mention very quickly that TCAE is special because it's unlimited in terms of number of its users. Limitations, there are no limitations in jobs and cores and the hardware installations. So it's quite attractive for these reasons, because the users can use their resources to the fullest. And it's definitely accurate because it has clear focus. It's focused. It's aimed on particular workflows, especially it's aimed on turbo machinery simulations and at external aerodynamics. So for this reason, it's aimed and it can be accurate. It's definitely not a general purpose code. Here at CFD Support, we are obsessed with the accuracy. We believe that any successful project is a result of skills, experience, patience, and dedication. So it's a quite big deal to do the simulations for the industry. And there are a couple of benchmarks we associate with TCAE, and we are ready to show them, as you can see in this webinar. TCAE is highly automated. and at the end, it's the user who decides how deep to dive into the problem or not at all. So it can be used as a black box or as a highly sophisticated CFD or CAE simulation tool. It's the user's decision all the every time. And yeah, it's always under the development. We have a couple of ways. We think in the horizontal way, in the horizontal direction. We think about it in terms of new tools, new simulation plugins, new modules, and the complexity. And in the vertical direction, we develop TCAE in new applications, capabilities, and high-tech methods. And in February, we had a new release, which was quite big, and we are already working on the new release, which will be released in September this year. And we are even working a little bit in the very next release which is scheduled on February 2022. Okay. Anyway, time for the simulation part. So Radek, can you take over, or I will?
Yes. So just can you give me the presentation? Okay.
Yes, I will. So I'm doing it right now. So I guess we can see your screen. So you can,
okay, perfect. Okay, so thank you, Luboš and Daniel, for the first part of the presentation of this webinar, and I will finish with the simulation part. So at the moment, my work is much easier because I will just take the Pointwise mesh and I will import it into the TCAE environment, and I can pretty quickly set it and use it for the simulation. So just for your information, all the details about this Potsdam Propeller benchmark or test case can be found on this SVA homepage, and you will find all the resources, all the source geometries, setup, simulation setup, and the measurement details. Yeah, so this can be found here, and the particular TCAE case you can find on our web pages under the Potsdam Propeller section. Yeah, so you can check it by your own and possibly try it by your own. So let me jump back into the graphical user interface of the TCAE. So I will not go into much to details, but I will quickly show you the workflow, how to load a prepared and high quality mesh from the Pointwise. So TCAE consists of several components, and the component which takes care about the meshing or importing the meshes is called the T-mesh. And in the setup part, there are just few sections to be used for reading the external mesh. So first part we need to take care is just to set a proper axis of rotation, and let's say some kind to define the rotation and or rotational symmetric parts of the mesh. So here we simply set the axis of rotation and the origin point on the axis. Then in the components, because we have one rotating and one non-rotating component, so we create two components, and here we simply choose the proper mesh input. So Pointwise has a capability to export the mesh directly into the OpenFOAM format. So we can take the OpenFOAM format, export it from Pointwise, and directly load it here. So we will just locate the directory in which the OpenFOAM mesh is stored, and then it automatically loads the given part here. So the first part is the stator part, which consists of the inlet. So maybe I can extend it. Yeah, so here's the visualization of the axis. I can delete it, and so basically we have several patches, which is already defined in the Pointwise part. So we have inlet and outlet. We have the outer cylinder or the domain of the flow channel. and we have the stator part of the stem of the propeller, and we have an interface to the rotating part which encloses the propeller itself. And then we have the second component. So again, we just use the external OpenFlow mesh, locate the particular mesh. We set it as a rotating because this part will be solved in the rotational framework, and then everything is automatically loaded. So all the parts of the propeller we can see here. So we can visualize each part, and of course the blade itself. All these parts are set as rotating, and basically that's all what we need. Yeah, the only part which has to be done is to connect these stator rotor interfaces. So we can just click using the right mouse click and connect it to the proper stator interface from the rotor part. Yeah, now here we have just one couple of interfaces, so we just basically set to the only option here, and that is all. Yeah, all the other options are connected to the direct meshing with SnappyX mesh, but for the external, for high quality meshes on the particular applications, it's always great to have some external meshes to be loaded and use your high quality mesh, as in this case from the Pointwise. And then we can come to the simulation setup itself, and it is always the same. Yeah, so in here we have a particle simulation type propellers. So for simulating propellers like here. Then here we set several points on the speed line to follow the measurement data. So we will simulate different physical conditions with different flow rates or different speeds of the flow to generate the full performance map. We set the physical parameters following the experiment, so some reference density, dynamic viscosity of the water at the given temperature, and so on. For simulation, we use the K omega SST model. We use the rotation of 900 RPMs as follows: the experiment data, and of course additional setup for the post-processing, for the solver setup, how we will evaluate the efficiencies, thrust and torque coefficients, and so on. Of course, the details about the solver itself, but usually you can keep them on the default values. Boundary conditions, particle boundary conditions are here set by the inlet velocity vector. Yeah, so this follows the particle experimental data. So then we can directly compare given points to the measurements. At the outlet, just a fixed pressure with zero relative pressure or reference pressure is set at the outlet as for standard incompressible simulations. Because the mesh is nicely resolved, as Daniel showed us, so we are using the low Reynolds wall functions for each wall part. The connection between rotor and stator is done by AMI, or basically it corresponds to the frozen rotor, and some reasonable guess for the initial conditions. Then few additional steps for the report. So what are our preferences for the units? What we would like to evaluate in addition, some blade-to-blade use or meridional average, or any other post-processing and miscellaneous parts can be set here for additional export. And so the setup, if you follow the measurement and the test data, so you will set up pretty quickly. The mesh is loaded pretty quickly, so then you just need to run the simulation. So I will jump in time a bit, and when I took which is here, yeah, so when we run the simulation and everything is ready, or before we run the simulation, we can visualize visualize the mesh which is imported. So basically Daniel will already show us the topology and explain how it is generated. So we simply just take it and run the simulation. Yeah, so we can go here, go to the general section, we can define the directory name and hit the run all button, and everything is run automatically, all the steps. And whenever the simulation is finished, an automatically generated report is generated where we can read all the data. Yes, like some simulation statistics, some statistic about the mesh, about the Y+. What is new in our new version is some simulation score, which shows you if some criteria are satisfied, and if not, you should be a little bit careful about the results. So then you should check if some boundings or if the residuals are not converging well. It will show you some indicators like in the orange warning or in red some kind of, or be very careful of the results. So sometimes it may happen that the simulation is not converged well. So you should recheck the input parameters if everything follows the physics of the machine and so on. We can read also some simulation statistics. So the simulation took almost 2.5 hours on the 96 core machine. We used second order numerical scheme, and now what is the main output is this performance curve, which is a typical output for the, let's say, for the proper simulation and propeller analysis. So in one graph we can basically see the efficiency of the propeller and thrust and torque coefficients. So we can then take this data and compare them with the measurements. So this we have done. So if you go to the Potsdam propeller and see the PDF report, which is opened here. So here you can read about this test and about this benchmark, and basically at the end, so these are the main coefficients, yeah, so the formula for them, and as an output we can see a nice comparison between the measurements and the TCA simulation results on Pointwise mesh. So we can see very nice correspondence with the measurement data. So this is really brilliant results of the solver from the TCA and for the mesh generated in the Pointwise. Yeah, so basically you can play nicely. So you can really validate the solver like here. So we did several meshes. So several meshes with different refinement, and finally we go to the finest mesh which Daniel showed us on which we got really nice result with pretty awesome accuracy. Additionally, what we can do, of course, we can then after the simulation we can have some visualization and analyze the flow pattern particularly. So we can combine any filter which ParaView provides, and we can visualize all the details, all the fields which TCA stores. Also, there is some cavitation indicator, but the simulation is not focused on the cavitation itself. It's just an indicator where the cavitation can occur. Yeah, so it's just kind of post-processing for the steady-state solver. All right, maybe the last thing to do is because this version of TCA implemented also the FEA analysis. So we can simply take the results from the CFD, and we can use some kind of FSI simulation for the finite element analysis. So we can also analyze the solid of the propeller itself. And as a result, which we can see here, is, for example, the displacement analysis. Yeah, so you can, for example, you can visualize the displacement on the highest load of the blade. And you can also, as I will show you in few seconds, you can also analyze or perform a model analysis and see what are the frequencies, eigenfrequencies, and so on. So this is typically two main outputs. So the displacement, then of course the stress. So we can locate where the highest stress occurs for the propeller, and if it in the range of in the correct range to be able to work at the given conditions. And you can also see some displacement for the model analysis, yeah, for eigenfrequencies, what is the stress and so on. This can be done in the GUI. So let me check. Yeah, so this is the setup for the finite element analysis. So you will just tell I would like to use the fluid structure interaction, from which patches I should map forces from the CFD. If I would like to also provide a model analysis with given number of eigenfrequencies, and then you simply run or you simply add some additional basic parameters of the solid, and you run the simulation, for which you get also the HTML report with the tabulated values connected to the static analysis and to the frequency analysis. So you can see the eigenfrequencies and so on, and some participation factor which is connected to the model analysis. All right, so I think that's basically all from my side. So what I would like just to emphasize that the importing the external mesh is really job for several minutes to import it, to load it, and then the process for CFD simulation or FEA simulation is very similar to all the cases whenever you are using the inbuilt mesher, which is open4mesh, or if you are using any external meshes. And as we can see, yeah, the output of these two softwares, both Pointwise and TCA, is brilliant, and you can really get an outstanding results using these two tools. So I think that it's all from my side, and I will give the presentation back to Lubos. So,
all right. Thank you, Radek, for your contribution. It was great. Thank you. So I'm taking back the screen, and I guess, can you see my screen now?
well, yeah, there is the welcome screen now. Yeah, so
Welcome.
We don't see your monitor yet. Yeah.
Okay, so maybe something have gone.
Yeah, I
wrong,
think we should wait 10 or 15 seconds
more.
more.
Okay, I see. So it's this typical issue. Okay, it's a couple of seconds. So yeah, so the beauty of this test case is it's a mix of turbo machinery and external aerodynamics, right? So it's an object which is rotating, but it's rotating in an open space. Despite the measurement was done in a tunnel. So in general, it's an open space, a marine propeller. So it's good, very good case for this reason. And yeah, I think it's time for you to ask your questions. So I would like to ask the audience to ask your questions, and we'll be happy to answer some of them. I'll ask my colleagues if my screen is visible.
Yes, it's on.
So you can see it now.
Yes.
Okay, perfect. So yeah, so now it's time for the questions and answers. So it always takes some time until the first questions start coming. So let's see. So yeah. So ask your questions. In the meantime, I will ask Radek, how much time would you guess it takes to run such a project? Because it still is a project, right? You start on Monday morning, and when such a PDF report is done, how much time it takes of your work?
Well, it's always hard to say, but you need to be really careful go through the benchmark and through the measurement, yeah, to really set the case properly. You need to be careful about the geometry topology, about all the setups and all the boundary conditions and so on. So you should be very careful what to set, because any changes in the topology, or if you maybe take some measurement for different open channel and not closed channel, then you will get different values. So you should be very careful, but if everything goes smoothly and smooth as possible, so it's a question of let's say several days, because you need to provide several iteration of different meshes, yeah, to see some mesh convergence on them, to take care about the topologies, take care about all the formats. So in general, several days for
Okay.
finish such a project when you know what to do. Yeah.
Yeah.
So.
And this case was quite clear, I guess, right? Was it?
Yeah, I think there was some, let's say, some analysis of the measurement and which data to take from them and which topology to use, because there are several variants for the measurements on the Potsdam Propeller pages. So you need to synchronize everything. But yeah, comparing to other projects, this was pretty clear. That's true.
Yeah. Okay. Thanks, Radek. A typical question again and again is yes, there will be a recording, and there is an automated system of this GoToWebinar which sends you the link for the recording, so that we will share it on YouTube. It will be pretty accessible. So don't worry, there will be a recording of this webinar, sure. And yeah, what else? Does anyone see a proper question to answer? Feel free to.
Okay, I see one question. Will you do a detailed setup for this case? So I feel we will be not recording it because the case is available on our pages, so you can download it and check how this case was set up. So there will be no detailed video recording about the setting up the simulation.
Yeah, but once again, it's the case is pretty transparent, right? Because it's all the resources are available. You can ask the trial version, you can run it yourself, check the results, double check everything. So it's very transparent for this reason. So that's the benefit of this case. Someone is asking, is it steady state or transient? It's steady state. It was simulated in the steady state mode. It's just steady state. So yeah, and as long as it was so okay in steady state mode, we I think, as far as I know, we haven't made any transient simulations, right?
No. Only when during the testing of the cavitation model, but it's not presented yet.
Right.
But
Right.
this was not the part of this benchmark.
Okay. Right.
And maybe I see another question: the gap between rotational part and stationary part is because of experiment, or there is a solver-related issue to have that? The setup was exactly following the setup and following our experience with the sizing of the rotating part. So the whole topology was really fitted to the experiment, and the sizing of rotational part was followed by our experiences. Yeah, so there was no issue with the solver.
Right. Yeah. Okay. Yeah, so now there's a couple of questions, so anyone feel free to jump in and pick a question, or yeah. Displacement. Yeah, and if you don't see any appropriate questions, I think we can move forward if you like. So what do you think? I guess we can. Okay, so that brings me to the last slide, and this will be really it. So yeah, we would like to thank you for your attention. Maybe some last word. Daniel, are you following?
I'm here. I had to find the button to unmute myself. So no, thanks for having us be a part of it, and thanks for inviting us to take part. I enjoyed it. I enjoyed making the mesh and seeing the results and how nicely they matched up.
Okay, it's perfect. So yeah, thank you for your support. It was great, and it was yeah, fantastic. And maybe yeah, so this will be it. So Radek, would you say some last words?
Just thank you to Daniel for a very nice mesh to be used within the benchmark, and thank you the audience for watching us. And if you have any question, contact us and we will answer the question which was not answered maybe during this webinar, or any other question after the webinar.
Okay.
Thank you and bye-bye.
Okay, thank you, Radek. Yeah, and so this will be related. I guess it's clear that the questions about Pointwise are about to send to an email or to Daniel, or to email sales@pointwise.com. The questions about the simulations are about to be sent to CFD support. So yeah, this would be really it. So we leave you with that, and bye bye till the next time.